All right, so as we're about to do a rotational problem, let's sort of flash back to a chapter 2 kind of problem. We have a car starts at initial velocity of 5 meters per second and accelerates uniformly at negative 3 meters per second squared for 8 seconds. What is the car's displacement? So if you flash back, we have displacement, initial velocity, final velocity, acceleration, and time. All we need is 3 in order to find the other two. Initial velocity is 5 meters per second. Angle accelerates uniformly at negative 3 meters per second squared, and time is 8 seconds. Find displacement. Well, we have a formula for that. Delta x equals VIT plus 1 half AT squared. And so that would be 5 times 8 plus 1 half times 3, negative 3 times 8 squared. 40 plus, let's see, it's 64, 32, negative 96, or negative 56 meters. Assuming I didn't make a math error. That's the basic there. Now, if we make it a rotational problem, we have a wheel starting with an initial angular velocity of 5 radians per second, has a uniform angular acceleration of negative 3 radians per second squared for 8 seconds. What is its angular displacement? Well, it's the same type thing, except we transliterate, so this is delta theta equals omega it plus 1 half alpha t squared. We have our 5 quantities, delta theta, omega I, omega f, alpha, and t. And so we know that this is negative 3 radians per second squared. Omega I is 5 radians per second, and time is 8 seconds. Plug and chug, and we end up with negative 56 radians. So the thing is rotating in the positive direction, stops, and then starts rotating in the other direction. So that's the basics of that type of problem. And I think we will end that there.